a very important area of mathematics. So let us try to understand this complex number from two perspectives. First is the mathematical perspective, and second one is the philosophical perspective. Okay, so we have natural number. Let us assume that we have natural numbers. Okay, the natural numbers 1, 2, 5. Okay, now when we are solving any equation, okay, any mathematical equation, we feel that there are also some equations of this type called x plus 1 equal to 0 or x equal to 0. So this necessitates that it is not that only natural number will be enough for me to solve my problem. So I need to have 0, and also I need to take the integers, which are negative numbers. So natural number, whole number, and integers all together, okay, will help us in solving the equations, linear equations to some extent. However, life is not simple. Okay, so in life, when solving the equations, we also come across 2x equal to 3. So 2x equal to 3, the answer is not, okay, the answer to this x does not belong to this set. Okay, so then we need to the mathematicians, they were motivated to find out what rational numbers. So rational numbers are the form of the form p by q, where q is not equal to 0. So this gave rise to rational numbers. And so you can see that now our set of numbers increased here, and it is 1.5 is not means only rational number is not enough in our real life. We also suppose you have a triangle. In the triangle, if the both sides, the adjacent side and the opposite side is made up of 1, 1, then hypotenuse is root 2. Root 2 is not a rational number. Root 2 is an irrational number. So now, so both now taking together rational number and irrational number, they form the real number. Okay. So now with this real number, we are able to solve the equations in real life to some extent. However, there is another problem. Another problem is that if there is an equation of the form x square minus 1 equal to 0, the life becomes very simple, right? We get x equal to plus or minus 1. However, on the other hand, x square plus 1 equal to 0, life is not simple. We need to solve this problem. Okay, we need to solve this problem. And how to solve this problem? So the people thought of means discovering or inventing new number, which is called the complex number, which is the imaginary number. So now you can see that you can see that complex numbers, the first, I told you that the first story is that in the real life, we have to solve so many problems, but in that it is not possible to solve all the problems, okay, whichever is arising. So there was a necessary for us to invent a new number system called as complex number system, and then we introduced this imaginary number system and then clubbed together with real numbers, where actually if a plus it is a plus ib, where a and b are real numbers. So this together gives the complex number, where I is equal to root of square root of minus 1. Okay. Now the first perspective which I told, the first story is that the complex number was introduced to solve the polynomial equations. Okay. Okay. Any polynomial equation has a root because complex number can also be real numbers. Like you can see here, a plus 0i is also a complex number, right? So now complex numbers are useful. So now this is the story that to make our life simple, to solve our problems, we introduce the complex numbers. Now coming to the second philosophical aspects of complex number. Complex numbers are very useful in representing phenomenon that has two parts varying at the same time. Please remember, please try to understand here that complex numbers are used to represent a phenomenon that has two parts varying at the same time. Okay, that means I have two entities. I have two entities which are real. However, I need to connect these two entities with some relation, right? With some relation. So that is the idea of complex numbers. I have some very interesting examples. The next slide will give you a very philosophical idea of these complex numbers. Okay. Okay. The next slide says that Okay, complex number. Now, whenever you say that, okay, now when you say the complex number, a complex number, whatever the operations which were applied on the real numbers, the complex number, same operation can be applied. So complex numbers act as like a bridge between two villages. Suppose there is a village 1, there is a village, there is a village 1, there is a village 2 here. Okay, so there are two villages that are located on opposite side of a river. If the nearest ford, that means if the nearest location which to reach the village is 10 miles upstream, means you have to you have to go upstream and then 10 miles, and then okay, then you have to reach the village 2. So from village 1 and village 2, in order to reach, you have to cross 10 miles, okay, and then reach. Now there are these are two entities. Please let us go to this slide again. Complex numbers are useful in representing a phenomenon that has two parts varying at the same time. Okay, so now I need to bridge these two villages with the help of a bridge, that is the complex number. So A is a village 1, B is a village 2. Now I need to represent this village by constructing a bridge between two villages, and this gives the philosophy of, okay, A plus IB, which is a complex number. Now, so yesterday I was discussing with my professor Nagbhushan sir. So he told me that, see, this bridge, okay, now why do you call this bridge as a complex number? The reason is that this bridge has magnitude. So any complex number will have magnitude. Magnitude means modulus of that particular. So it is square root of x square plus y square, gives you magnitude, as well as there is a theta associated with a complex number. Now this number, okay, this bridge has, why it is called a complex number? Because it has a magnitude, it has a direction associated with this particular bridge. Okay, what is the strength of the bridge? What is the orientation of the bridge? So that is the reason this bridge between two villages can be called as a complex number. Okay. So in order to tell a complex number, there should be a direction theta, and which is a tan inverse of y by x, and there should be a square modulus operation, means the length of the norm or length of the complex vector, which is square root of x square plus y square. And similarly, same principle is used in applying in designing the wings of the aircraft. So there are two wings of the aircraft on the left side and the right side, whereas this body of the plane represents a vector, represents a complex vector where it connects the wing 1 and wing 2. So that is how you can take it as A. So this body of the plane can be represented as A plus IB. So A plus IB, it has a magnitude, it has a direction. So we can tell that complex numbers. Okay. We use complex numbers to bridge the gap between the problem and its solution. Okay, so we use complex numbers to bridge the gap between I think I already explained you that why, what was the need for the complex numbers. Doing so does not change the solution. Now we should remember that what I have done is that I have only bridged two numbers. Okay, because those two numbers did not represent separately. I bridged two numbers. So now doing so does not change the solution. It is merely a convenient means of, okay, bridge. Okay, it is merely provides a convenient means, a bridge for obtaining the solution. Okay, I hope the idea of the philosophy of complex number is very clear. So yesterday there was a question when Professor Nagbhushan sir was giving the lecture that what is the real world example of complex number. I think this will give you a very brief, very philosophical idea of complex numbers. I have some more examples. So this is a very interesting slide, which I thought yesterday, and then I created this slide today morning. See, this is mother-in-law, this is son. Mother-in-law and son means the marriage of a daughter-in-law. Okay, daughter-in-law is very much connected to the property or the wealth what the daughter-in-law brings. Okay, so now this can be so mother-in-law, when she is looking for a daughter-in-law, then mother-in-law is focused on daughter-in-law should be beautiful also, along with beauty, which is, so daughter-in-law is real, whereas the wealth she brings when she comes to the to her house with the as a daughter-in-law, she also brings some property. Okay, so now this I think through this slide, I think the idea of complex number is very, very clear, that marriage is equal to, or mother-in-law m equal to daughter-in-law plus I times the wealth, the property what she brings. Whereas you can see that daughter-in-law is real, whereas this property is attached to daughter-in-law, okay, which is which is also attached to the mother-in-law when she's when she's married. Okay, so this property is a something which is imaginary way you can see that. Another example to make you understand, I have tried my best to collect so many things to make you understand the complex number. So another way to see the complex number is, you have a pizza. Okay, the pizza is made up of 8 pieces. Now, can a number be a combination of 2 numbers? So now my requirement is, you want to, complex number is a number, one entity, and for that one entity you are representing that one entity as a 2 entity, combination of 2 entities, a plus ib. Now you can see that the fraction, now to represent one number, like for example, to represent some number, one number, fraction 3 by 8 is a number which is made up of 3 and 8. So a number 3 by 8 is made up of 3 and 8. Okay, so this gives you an idea that I'm representing a number fraction 3 by 8 using 2 numbers. So I can say that means in a nutshell, I can say that 3. So I have to get one number, one entity, so that I have to combine 2 entities. So it is same thing. You can tell that a complex number is made up of 2 numbers. Okay, and 2 numbers I am combining to make it as a single number. So same way here, 2 things I am combining, daughter-in-law and money, the property, for a marriage or for a for the mother-in-law. Okay, so so like this. So you can see that it means there are so complex numbers are used in everywhere. Okay, everywhere there is a relationship between 2 entities. We need complex numbers to model them. Okay, so this is an just to show you that how f of x equal to x square plus 1 graph will look like. Okay, now when you plot, when you start putting the values into x value as 2, 1, 0, you can see that you will get a 1 graph. But when it is 0, the graph does not touch the x-axis. That means for 0 there is no solution here. Okay, for 0 there is no solution on the real axis. So this is one way of mathematical way of, or visual way of looking into the complex numbers. So there are in the literature I have found out that there are 3 ways to visualize the complex numbers. One is the Cartesian plane. Now I give you the example of a plus bi. A plus ib is it has a magnitude and it has a direction, and all the operations which can be done on real numbers can be done on these particular complex numbers. Okay, the other way of representing is using the polar form. Okay, polar, x equal to r cos theta, y equal to r sin theta. Okay, so r is square root of x square plus y square. This is the another way of representing, where x is real axis and y is imaginary axis. Okay, so now imaginary axis is same. Okay, the imaginary axis, you can take here the value is 1, here the value is -1, here the value is I, and the bottom the value is -I. So another way of representing the complex number, see, it is complex numbers are made up of 2 numbers. So I have gone through the literature, and people have said that it is very difficult to visualize the complex number in 2D plane. Okay, means visualize the picture representation of complex graph within 2D plane, and we require 4D plane to visualize this one. So people have tried to generate color wheel graph. Okay, they now see, this is a complex, this is a very a visual representation of a complex number with colors, different colors. So now you can see that here each color represents an one particular entity, okay, and we see that different colors are combined, and this produces a very different, very beautiful art. And yesterday's lecture we have seen that Professor Nagbhushan sir said that this is very wonderful. This is the in nature also we find these kind of complex drawings, okay. So and also recently I reviewed one research paper for the Journal of Pattern Recognition, and in that I also read that. So that is the reason I brought this slide here. Okay. Another way of looking at the complex number is actually the complexity of cells in the human brain. Okay. So visual cortex is the area, okay, back portion of our area, means the brain, which is responsible for doing all kinds of operations, like it is involved in interpretation, it is involved in recognition. I told you in my first few slides, I told you that cognition and recognition. So this is the part of the brain which helps you in learning features and also recognizing the the person or the object. So the reason is that here this part of the brain is made up of very complex cells, okay, where we can relate the what you call where we use the complex numbers, okay. We can use complex numbers to represent the signal which is generated from these cells. So this is one example that our human brain also uses the complex numbers. Okay, so I'm not going deep into that because of shortage of time. So you can, if you're interested, you can go more into the detail of this particular thing. And that research paper had cited this idea. So I thought that let me bring it here. And so the other very famous example, see, whenever you try to search about a complex number in the internet, this is the first example which you try to get it. Okay, so they try to explain you complex number with an example of a current. So a current is made up of voltage as well, means a circuit is made up of voltage as well as the current. Okay. However, voltage and current should go together. They are not as separate entities. So I represent these complex numbers this voltage and current as Z equal to V plus I. And now you know that same operations which are applicable for the real numbers are also applicable for the complex numbers. So now I can do so many kind of multiplication, addition, all kinds of operations I can do. Similarly, the capacitance and inductance, they are now coupled together as a complex number. Okay. See, in the same manner, okay, this is the second most famous example for complex numbers. If you try to search in the, excuse me. So if you try to electromagnetism, in the electromagnetism, electric field strength and magnetic field strength both go together. So they need to be combined as a complex number, right? So there are many, I think I have already explained this, okay, in different phenomena, different signals in the brain. Okay, signals in the brain are very complex, okay, and they need to be represented using the complex numbers. Okay, so so in future, because of more automation, digitization, so it is more complex number is going to be used in that particular scenario. Another very important, very famous example of complex number in the signal processing area is discrete Fourier transform. So discrete Fourier transform, which converts a frequency, a spatial domain signal, a spatial domain, converts a signal from a spatial domain to the frequency domain. Okay, now you can see that there is a, so this is a frequency example. Sorry, this is a spatial example where the signal is becoming positive, negative, positive, negative. If you take black as a positive, so this is a signal which is varying. Similarly, this is another signal which is varying. Now, when you plot this signal in the frequency domain or Fourier domain, you can see that this entire image is represented as 3 dots here. Okay, so these 3 dots represents 3 types of frequencies, right? Similarly, you can see that this is these lines are modeled as 3 points in the frequency. They are of the 3 kinds of frequencies which are modeled. So this is a very famous okay. So now the question is why to convert from frequency spatial domain to the frequency domain. So in frequency domain, like for example, a problem of noise removal is not possible, means it becomes very difficult in the spatial domain, whereas in frequency domain, the problem of removing the noise becomes a very simple. So, so the concept of transformation from one form to the other form, and now the main driving principle behind this Fourier transform is a complex number. Now you can see that I have already written this matrix. This matrix is used to convert spatial domain into frequency domain. Okay. This matrix is used to convert from frequency domain, spatial domain to the frequency domain, and this is the matrix which is most popularly used in the JPEG compression. Okay, I have, so now just to make you, so these are all numbers, right? These are all symbols. Now I am giving you a pictorial representation of signal. See, this is the DC signal. That means there is no fluctuation here, right? This is the direct current, whereas these are the alternating current. Okay, these are alternating current with different frequencies. So this is the visualization of this particular 8x8 matrix. Okay, so now what are the application of this discrete Fourier transform? So discrete Fourier transform, you can see that different you are modeling the time, you are modeling the signal into different frequencies, and now lots of applications in signal processing, image processing, heat distribution, wave simplification, light simplification, radiation measurement, data compression. You can name any field, everywhere actually DFT is used, because because DFT is very close to the human life. Okay, means like human being communicate with signal. My voice is communicated to you as a signal. My my face is communicated to you as a signal, right? So similarly, my heartbeat is a signal. Okay, similarly, everything in nature is a signal. So we need to learn from the nature and model it. Okay, so we need to model all those things, okay, in the real life. So another example which I want to show you is that discrete Fourier transform. Like for example, this is the image. I think yesterday in Dr. Pradeep Kumar talked about this one, like how to remove the noise. Like this is an image of the moon or Mars. I don't know exactly. So this is a moon. This is an image which was captured by the moon mission, and then we can see that when I convert this image into frequency domain, you can see that this pattern, which was a noisy pattern, it is just some symbol. Okay, just some frequency. I use this frequency domain filter and I try to remove this noise. So you can see that this particular regular pattern is being removed from this particular. So this is application where discrete Fourier transform. So now the idea is that Fourier transform is driven by complex number, and that complex number is now helping us to solve different kinds of problems. So another very important problem is JPEG compression. Okay, I have 15 more minutes, so I would be a little bit faster. So JPEG compression is a very popular compression algorithm. I already have given you one example there. So JPEG compression uses 8x8. Okay, it compresses the image by dividing into 8x8 blocks. 8x8 blocks. Again, this JPEG uses discrete Fourier coefficients. Okay, discrete Fourier coefficients.
Hey, Javed.
Ma'am?
Hello.
Yes, ma'am.
Sorry for interrupting, Javed. You can take your own time. If you need additional time, you can just take.
Okay, ma'am. I will just come. I will try to give as much as input, ma'am. Okay.
Yeah.
Thank you.
Thank you.
So this is a JPEG compression. You can see that lot of there a lot of see, I'm not going to explain you in detail, but my whole intention of this slide was to tell you that discrete Fourier transform drives you the most important application of JPEG compression. Okay, so I take the pixel and then I multiply that this pixel, this 8x8 pixels is multiplied with the coefficients, DFT coefficients, and then you get the different frequency. What you call this is this matrix. It gets multiplied with this matrix. Okay, with this matrix, and then we generate coefficients, and these coefficients are called the Fourier coefficients. And in case of JPEG, it is not directly Fourier transform, because JPEG uses discrete cosine transform. It does not use sine wave, because see, the main idea behind the usage of cosine transform in JPEG is that 0, 0 value, the value of cos function at 0, 0 is not 0. Okay, cos of 0 is 1. So that is why, see, the most important signal in JPEG compression or discrete Fourier compression is actually the direct current. Okay, that is the DC value. So if you use sine value, what happens is that you are going to lose the, if you are using the sine value, okay, sine transform will not give you DC current, because sine of 0 is 0. So JPEG compression uses discrete cosine transform. Okay, discrete cosine transform for compression. So if you go through in the literature, you can find a big formula based on these JPEG compression. Okay. So now coming to the recent state of the art literature. Okay. Now, a very important application of complex number, which we being in the area of machine learning and deep learning have found out that now people are trying to use complex numbers in deep learning. So this is a very, I have reviewed, I think that brain image which I have put, okay, in my slide. That image has been taken, okay, that idea, the paper, actually the research paper proposed a complex number for removing noise from an image. Okay, so now people are now moving towards using more and more complex numbers, because we know that complex numbers is not just one number. It combines two important components together, and it tries to give you the tries to give you the feature extraction, this okay, feature extraction, modeling, and all those things are possible. So complex numbers are used in image analysis, okay, noise removal. They are used in radiology. Like for example, they want to analyze where the bone fracture is, where they want to analyze where the tumor is. All those things are possible using the radiology. And then we have EEG pattern. So EEG pattern also uses complex numbers for analysis. Similarly, you have, if you go through the internet and Google it, you have tremendous applications which are actually, see, I'm telling you, this is the state of the art. Deep learning models are the state of the art models in today's machine learning. In whatever automation you tell, they are the state of the art. And now the usage of complex numbers is giving them a new dimension of research. They are getting more accuracy, okay, and all those things are possible. And one more very important thing, I was just forgetting it to mention, that the complex model, the complex number model, is more memory efficient, and vanishing gradient problem is solved. Means it reduces, because if you are gone through deep learning, you will see that the vanishing gradient problem is a big problem, okay, which disturbs you in okay, optimization. Then the complex number gives you very good vanishing, means it reduces your vanishing gradient problem, as well as it makes your model more memory efficient. So another very important, very wide application of this one complex number is used in the fractals. So a fractal, let me define a fractal. I think yesterday you saw a few slides in Professor Nagbhushan sir's lecture. So let me, so now I tell you that, see, yesterday you saw only picture, but today I am telling you that this picture is derived from complex numbers. Okay. So a fractal is a never-ending pattern that repeats itself on different scales. So when you see this, fractals are very popularly found in what you call, I think in the snowflakes. I don't know, I don't remember the exact word. In snow, if you try to zoom and zoom, so there is a separate book, textbook written on fractals. So if you go through that, the fractal. So fractal is a never-ending repeating pattern that it repeats at different scales. Okay, same pattern. While the fractal itself can look extremely complex, the initial shape or the item to be repeated is often extremely simple. So this is the one basic example of complex numbers to represent fractals. Now you want to represent this fractal, so you need to use the okay, complex numbers. So now you can generate these fractals by visualizing the complex numbers. So two way. Now you have a complex number you want to visualize, then you can generate fractals out of that. These are some of the, yesterday also you saw some slides related to this one. The objects in the nature develops its shape using complex numbers. Okay. Okay, so now this is a best example that your complex number has very wide application. The nature also thinks, that is why, like we are, see, the main motivation is that in nature we find equations which require complex number to be solved, right? So same way, the nature is also made up of different nature is also made up of different objects which require the complex number representation. Okay, the kind of objects which I've shown here. Now, the complex numbers are also used in control theory. So I am not an expert in control theory, so I would not go much into the details, but I can just tell you that in control theory, everything, like for example, communication means all the objects, all the different entities need to be put together and bound together, and that is how the control theory is. Okay, complex number is used in the this one, what we call the control theory. Okay, so they need to be clubbed.